This video shall walk you through figuring out the electric field, the net electric field midway between two given charges. So this is not a charge in somebody else's field. This is two charges. Each one creates an electric field, and those two electric fields will clash, and we will find out what the result of their clashing or interference, if you will be exactly midway between the two charges. So first off, you need to figure out where the midway is. If the two charges are 10 centimeters apart, as shown in the diagram, then my midway will be 5 centimeters from each. Then, once you figured out your middle point, then you're going to figure out, okay, so I have two charges. Let's look at the electric field caused by each one separately. Remember, the direction of the electric field is the direction of a force on a positive charge. So you imagine a tiny positive charge at this point in space. What will the negative charge do to it? It will attract it. So I will say this would be my E from the -3. Then +3, a positive charge would be repelled by a positive charge. So this field, which will be from this charge right here, would also point to the left. And it's going to be right here marked as E of the +3. And I'm just being lazy, not writing nanocoulombs, but that's what is meant. Now, the formula for a field caused by a charge, as you remember, it's like a reduced formula for electric force. Electric force we had as Kc, and then we had Q1, Q2 over R squared. Now, if we are figuring out the field, we're losing the charge, and we just keep one charge, the charge that made the field. And I'm using the big Q just to tell you that it's not an imaginary tiny charge in the field, but the field created by that charge. So that's the mother, sort of mothership, if you will. And the distance to that charge from the point you're looking at. So in our case, since the charges are 10 centimeters apart and it's midway between them, then this will be 5 centimeters. And then when you convert that, remember you have to convert to meters, that will be 0.05 meters. Now, as far as the value or the magnitude of the charge, since both of them are 3 nanocoulombs, then those two vectors are going to be identical. So I don't really have to count it twice or calculate it twice. So I'm going to do it just once. I'm going to find one electric field, and then I will double it because I will add them, not subtract, because they're both in the same direction to the left. Kc being 899 10 to the 9th. 3 nanocoulombs. Again, it's an absolute value. The minus tells you it's going to be towards the charge. The plus tells you that it's going to be away from the charge. It's the direction. So I don't have to put a minus in front of 3 or plus. So that's 10 to the -9th. And wink, wink, that's why I gave it to you, so you can cancel this. And then I personally like doing 25 times 10 to the -4th. Now, where did that come from? That came from 0.05 being 5 times 10 to the -2. And when you square, that becomes 25 times 10 to the -4th. Okay? So then I can just do 899 times 3 over 25, and then times 10 to the 4th, bringing this one upstairs. That's how the 10 to the 4th comes up. Now, then I remember that I need to double this. So times 2, because there are 2 of them. And then you just plug this into the calculator. So that is 2 times 1.1 10 to the 4th. So basically 2.2 times 10 to the 4th. And remember, newtons per coulombs, that is the value, that is the newtons per coulombs are the units of measure for electric field, because by definition, electric field is how much force is applied to a charge in the field. So it's force per charge, newtons per coulombs, not to be mistaken for nanocoulombs. So that's the first example. Second example. In the second example, both of our charges are positive. So therefore, let me just zoom in. You know the question. So it's the midway between the two charges. Midway being at 0.1 meters. So 0.1 meters would be our R. Then if I put it here, this would be the field from 3 nanocoulombs away from the charge. And this would be double because the charge is double. Distance being the same, this will be the E from, sorry, this was E from, and this is E from 6 nanocoulombs. There we go. So then ultimately, you're welcome to find them separately, each one. So you would do 8.99 10 to the 9th times this, and then just up here you would put 6 nanocoulombs and 3 nanocoulombs. Once you figure those out, you can subtract. That is one way. I'm just going to simplify this way more to save the time. So because they're both nanocoulombs, I put 10 to the negative 9th right here. And then I know that this field right here is going to be greater than that one to the left. So I'm going to end up subtracting the field to the left from the field to the right. So instead of doing it several times in a row, I'm just going to do 6 minus 3. That's your subtraction right here. And that reduces our work to 899 10 to the 9th times 3 10 to the negative 9th over 0.1 squared. And just like before, here's some simplification because 10 to the 9th and 10 to the negative 9th is the same. Then we do our 899 times 3 over 0.1 squared. That gets us 2,700 newtons per coulombs. And we're going to say to the right, or you can just do 2,700 newtons per coulombs. Bzding. Shows us that it's to the right. So that's the answer to the problem where you have 2 positive charges. The bigger one is on the left, so therefore its field is going to overpower the one to the right. I mean, sorry, the other way around. The field from the left charge pointing right will outpower the field from the charge on the left that was pointing left because they're both positive. The next one is both negative, and midway will be at 0.15. And just like before, instead of doing it one at a time, I'm going to subtract the 2 charges. But before I do that, let's decide which way does it look our field is going to be pointing. This would be the field of negative 9 because remember the field is the direction of the force on the positive charge. If you imagined a baby positive charge right here, it would be attracted to the 9 picocoulombs. And it would also be attracted to the 3 picocoulombs. It's going to be 1/3. So I'm just going to try and show that it's 1/3 of what it is. It's okay if you don't really. I didn't. It doesn't have to be exact. I'm not going to take a ruler and figure out that is it really a 1/3. This is not a graphical solution. This is calculations. So then we're going to do 8.99 10 to the 9th. And our distance is 0.15 squared. And then you do 9 minus 3. So overall, and it's 10 to the negative 12 because it's picocoulombs in this case. So we're going to do 8.99 times 6 times 10 to the negative 3rd, because when you do 10 to the 9th and 10 to the negative 12th together, these two, 10 to the 9th and 10 to the negative 12th, together they will give you 10 to the negative 3rd when you multiply them, because you add exponents, over 0.15 squared. So when you put that into your calc, 0.15 squared, and then times 10 to the negative 3rd, you move your, it's going to be 2.4 newtons per coulombs, and it's pointing left towards a greater negative charge. So this is a video on finding net electric field midway between two charges.